Hello everyone, welcome to my pathfinding video. This is going to be an overview where I'll have a follow-up video where I'll go into the code, show you what it looks like in action, and a specific example that I was able to implement. This is a point where we start delving into some of the hard computer science, specifically graph algorithms, those pesky graph algorithms. If you've had some computer science algorithm classes before, you might remember a chapter on graph algorithms that were maybe not as interesting to you at the time. Maybe you can revisit that after this video and after you start messing with this yourself to see how you can actually get some use out of that concept. So, pathfinding those pesky graph algorithms. So, what is pathfinding? It is finding the way to get from a point A to a point B through some complicated level world graph so that you don't have to always do it by hand. Now, when we have the player in control of something, it's easier for the player to look and intuit and navigate through and how to get to a goal. But we don't always want to have the player handle all of the intricacies of navigating a complex mesh. In fact, we'll probably want, at the very least, enemy agents to be able to find the player wherever the player happens to be and be able to traverse terrain without getting stuck on walls or clustering in corners. Or maybe you're designing a game like a real-time strategy where I just want to select a whole bunch of units and tell them to go to the enemy base, and I don't want to have to tell them how to get there. There's a lot of different ways we would need pathfinding for different games. So let's see what some of the classic approaches have been. So as I mentioned, the whole field of graph algorithms is what we would reach to in order to find a path. Now, most classic examples look and describe the graph as something like this. It is a series of nodes and edges connecting the nodes, a vertex and an edge connecting them in a kind of a mesh. And if we want to be able to find from point A to point B a way through the mesh, there's a lot of different approaches that have been developed over the years to help us figure that out as efficiently as possible. The simplest brute force approach is a breadth first approach, where we're going to, starting our initial node, add our neighbors to a to-do list, and then iterating through them one by one, checking to see if either of them is the goal. And if none of them is the goal, then each of the neighbors of the next node recursively is going to add a bunch of nodes to our to-do list until we find our node, and then we can backtrace from our end goal to each of the nodes that we took to get there, and that'll find the approach. Breadth first is generally considered inefficient for certain shapes of graphs if they're not widely distributed. It's going to require us to go through pretty close to all the nodes possible in order to find our goal. Contrasting that is the depth first search, where we will pick our starting point, check to see if it's our goal. Then we will add each of our neighbors to the to-do list, and then we'll hop to one of those neighbors, and then from here we'll check to see if we're the goal, and then we'll add each of our neighbors to the to-do list, and then we'll hop down that road, and then we'll add our neighbors to the to-do list, and you'll end up, as long as you don't repeat any nodes, eventually finding it guaranteed. The Dijkstra's algorithm is basically depth first search, but each of these connecting lines doesn't necessarily have to have a even weight. So what we end up doing is we'll pick which node to go to next based on the one that has the smallest weight. Now, what I mean by weight is we can say the cost to traveling that road could be higher than others. If we think about a real-world road system, think about like how our maps, our GPS systems end up giving us paths to get to our goal. Not every road is the same. Some of them are slower, they have lower speed limits, some of them have more traffic lights. Real-time traffic information could be affecting what the weights are, which roads we choose, which roads we avoid. So that's the Dijkstra's approach. A-star takes it a step further and adds it in a heuristic, which takes into consideration weights if they apply. But then we try to pick the node to look at next based on the one that seems to be most likely to reach our goal. And that could be as simple as which one is closer to the goal. So in this case, I would never check these nodes being further away from these two nodes, because they're unlikely unless I exhaust my search, and for some reason, like I say, if this line didn't exist and this line didn't exist, I would check these first, fail, and fall back to the next best one, which would be this one, and then the next best, and the next best, and then we would get there, like so. All right, so how do we actually start putting this together? Particularly when we're talking about a tile map. Now, I look at a tile map, and I'm first looking at these graph algorithms, thinking how I could use this on my tile map, and I'm thinking, like, the edges don't make sense, and the nodes, like, I don't want to go to the intersection of 4 tiles. That doesn't make sense. I want to go to the center of the tiles. So the actual approach is to consider each tile is the node, and the edges that connect them are adjacency. So if I have two walkable tiles next to each other, the edge would exist between them. If I have 2 tiles that are not next to each other, or blocked in this case, I would just not consider this node, and I wouldn't have an edge here. So when I start adding neighbors to my list, or children to my to-do list, I'm just not going to do that. So let's talk about what that algorithm actually looks like when we put it into play. Let me add one more slide here. The actual algorithm. So what we're going to do is, starting from the initial node with a goal in mind, we're going to, in loop, check to see, well, we're going to have 2 lists. Now, in algorithmic textbooks and on the wikis that describe them, they will use the mathematical notations for things like F and G and H to determine what the variable names are. I am of the new school as I approach this and think, well, I have a computer now, I'm not writing this on a chalkboard. So rather than have a code I have to figure out, I'm going to name all my variables something that's descriptive. So I'm going to have 2 lists. I'm going to have a to-do list and a done list. On each of these lists, we're going to keep track of the nodes. The nodes need to have, let me pull this over here. The nodes are going to have its position, its parent, its depth or cost to get here, and the distance or guess for how close we are to the goal. So this is what we'll, each one of these is going to be put in these lists. So starting with the initial node, we'll add our start position to the thing, and then we're going to, in loop, ask these questions. Let me shrink this down for some space. So the approach is going to be, for each node to do, we're going to check, is it the goal? If it's the goal, we're done. And then what we do is we look at our goal, and since we keep track of our parents for each node, if I was at this tile, my parent tile, if I can click on it, would be this tile. And then its parent would be this tile, and so on and so on and so on, to how we were added to the to-do pile. If it's not the goal, add the node to the done list. Sorry, I'm just going to get some space here. We keep a done list to make sure we don't check any tiles twice. There are some variants of A* where what we will do is, if we find more than one way to get a tile added to their to-do list, if it's already been checked or if it's still in the to-do list, but I found a faster way to get to it, I might recheck it because it would change its weight and where it would lie in the story. But I'm getting ahead of myself. Then we're going to do is add our children to the list if not already added. And then we repeat. So this is actually a remarkably simple approach once you wrap your head around it. So for each node in our to-do list, we are going to, let's take a look at what this would look like. So starting here from our starting position, I would add my node to the to-do list and I would begin. Then, am I the goal? No, I'm clearly not the goal. All right, add my two neighbors to the list, this one and this one. And then each one is going to be given its depth. So the first one was depth of 0, it's our starting position. These each would have a depth of 1 and a distance of, now you could either do this by cardinal distance or a Manhattan distance. So count how many across and how many up. I could do the Pythagorean theorem to give my absolute distance. Might be a little bit cleaner that way. Harder to explain though in graphic form when I'm walking through it now. I would pick one of these then to check next. So in this case, I would say pick this guy next. And this one would have a depth of 2, and it would add its neighbor depth of 2. And it would probably pick this one next, which would give us 3 and 3. And each time what we're going to do is we're going to pick the ones from our to-do list that have the smallest combination of weight to get there and distance to the goal. So eventually we'll start directing toward that, where maybe the next one I want to add is maybe this is the one that is now slightly smaller than that one, particularly if I'm using a raw distance as opposed to like a Manhattan distance. I would then add this one and none of these, maybe this guy here. So we add 5 and 5. And maybe this one gets picked, and then we would add 6 and 6. And then one of them gets picked. Doesn't matter because they're both going to add 7. Maybe that one's 7. And then we start backtracking. So then we find the one that is, of the ones that we have left, these to check, we end up with, say, this guy or this one. So this will then add, actually this would have been 6. And this 4 would add a 5 there. And this 5 would add a 6 there, and a 6 there. And then this one, at some point, might get checked. It's a 7. 7, 7. And we end up going down the road until, let's see, 10. Now, 10, but change the font size. There we are. And then 11, smaller font. And then this one would probably be checked next. But it would obviously not be able to add any more children to the to-do list. No, I'm shrinking the hole. There we go. And then so on and so forth. These will both get added, but this will probably never get picked. And it leads us toward the goal. So I'm going to leave this discussion to stop at that point. So that's the algorithm in action. This is what it looks like narratively. I mentioned the word heuristics. This is a fancy word for saying our best educated guess based on the information that we have. It's just a way of adding a little bit of filling in unknowns the best we can, and guessing and checking really is what we're doing with this approach. I was saying in this example, maybe we're doing the Manhattan distance or the Pythagorean distance. You could possibly even do like a line test from point A to point B, or from any node that we're going to do, and see if one or another happens to have more blocks in the way or not. So that could be a weighting factor. So at some point, this node gets added, and we have less blocks in the way of our goal. And so maybe that's the one we want to go with. It might be wrong. Again, the best thing about heuristics, it doesn't have to be right. It just, hopefully, if it's optimal, it'll mean we check less tiles overall before we reach our goal. If it's inoptimal, then we still will find our goal, just a little bit slower. This on sufficiently large node maps can be problematic. It can take time, particularly if I'm doing like a a distance that has a square root involved in it per tile, it can get complicated. It can be slow. And if you have a game like a real-time strategy game, like say imagine something like StarCraft, where I have hundreds of units that all need to pathfind, it can end up slowing the game down. There are some solutions. We can approach that. Pre-baking, what basically means is you pick some random tiles. So like say every 10th tile will pathfind to every other 10th tile. So I'll have like a list. So wherever I am, I would search through my list to see what the path is from my current position to my end goal. The worker thread approach, which I kind of have illustrated here, where I have the pathfinder that will take work requests as a separate thread. Now, so I'll have one thread over here, the main game thread, and this thread over here running concurrently, mostly busy waiting. So that what the pathfinder thread does is it checks a request queue that it can only read from, it can't write to, and sees if it has any unhandled requests. And if there are any unhandled requests, it'll start pathfinding and throw the pile on the done pile. Each request will be given an ID number. So basically it's like at a deli counter where each client is going to take a number. So I'm request number 17. And then the pathfinder will say, all right, here's request 17. I create a path. And on the done pile, we throw the path with its identifying tag, its ticket, on the done pile, and this is something that this can only write to, and this can only read to, and then this is something that only the main thread can write to, and only this can read from. And then during the entity's think functions or update functions, it checks to see, hey, do you have my ticket ready yet? No? Okay, order 16 has been done, but not 17. Eventually it gets done, and then the path client can then have it and go about its way. Other things you might want to consider too is that the done pile doesn't necessarily need to be cleaned. If I have a strategy game where I'm pathing a lot from my base and my enemy base, the path probably isn't changing that much. So what I can do is I can just leave these paths in my my done pile, and anyone who wants to find a path can just match on the done pile, and only if it's not already done do I request a new path. Another approach that I've seen described is you divide your grid up into regions, and then each region knows how to path to the next region. That's actually something that might optimize with the approach I'm going to go into next, because I modeled, if you watched my dungeon generator video, I modeled a dungeon as a series of rooms. So I don't need to figure out the path from every tile to every other possible tile. I just need to figure out how to get from room A to room B. And it is a much smaller graph that way. All right, that's all I wanted to cover in this video. I will be going through some code examples in the follow-up video and show how it looks in action. All right, thanks for watching.